Okay, thank you, Jackson. Like I said, he couldn't join us today, but he dug into the theory behind lifting line and was able to come up with a numerical method that could be used for winds with sweep, because the traditional numerical method, as he showed, is not very accurate for winds, for swept winds. So now we're going to turn the time over to Corey Goetz, who's with us online. He took this theory that Jackson had developed in and wrote a code based on it called Mockup. He's going to introduce us to Mockup.
All right, can you guys hear me?
Yep.
All righty. Give me a moment. I'm operating off of two computers today. Let me share my screen with you on my other computer. All righty. Hold on a second. Oh. Zoom always goes to full screen. Okay, here we are. Well, as Dr. Hunsaker said, I'm going to be talking about really the implementation of what Jackson accomplished. This resulted in a software tool that I developed called Mockup, and it was used, as you've heard, in a bunch of these different investigations to be able to model various wing geometries and study their aerodynamic performance and whatnot. Our goal with developing Mockup was really to make it something that was widely usable. You know, we didn't want this to just be kind of a one-off in-house code that we could use for a couple different use cases, but really wasn't, you know, widely applicable to anyone's general case. But so again, we've tried to make this as general as possible. It's all open source. It's available on GitHub. This is the main project page. You can download the source code from here. Along with being open source, we've have it fully documented. So we have a website that documents the code. And you can, you know, it's got instructions on installation, user interface, how to create input files, the units that it uses, the methods that are available. All of that good stuff is right here, available for anyone to use. We also have an active Google group. So a group of users in the aerodynamic community that are using Mockup and providing feedback to one another to be able to better use it. Just to demonstrate that, I'll show you. If you go to Google Scholar and just search Mockup, you'll get quite a few hits. And I'll give you a brief overview of some of the papers that or some of the research that it's been involved in. This is one paper coming from the University of Michigan, Dan Inman's lab. Dr. Hunsaker and I collaborated with one of his PhD students to use Mockup studying birdwing aerodynamics. And they did some wind tunnel testing in there and some pretty extensive validation of the results that they got out of Mockup. This is a thesis from the Naval Postgraduate School using Mockup to model the aerodynamics of a B-52 bomber type aircraft. This is a thesis from somewhere in Scandinavia that they used Mockup to do some control problems for unmanned aircraft. This is one that I had the opportunity to collaborate with a researcher from the National Research Council of Canada, using Mockup to say, you know, if we've got a desired loading distribution, here's the geometric twist you need to have on this swept wing in order to get that loading distribution. And then these are papers that have come out of Utah State using Mockup for different things. Bruno, you heard Bruno's presentation. This is one where we use Mockup to be able to estimate aerodynamic parameters of an aircraft based on certain position data. Zach will be talking about how he used Mockup for control allocation and mapping. And then, of course, the design of our 3D printed morphing aircraft that was done using Mockup. So again, I think we've accomplished our goal of making this something that's, you know, widely applicable and something. I think we've created a real valuable tool for people to use based on this money that we've received from the Navy. I'll show you here. This is the draft version of a journal paper that is currently in review that Dr. Hunsaker and I wrote, discussing the implementation of Mockup. There are a few nitpicky things that are different from what Jackson did. But I won't get into that. That's all very heavily theoretical. I do want to take you to where we just compare to some experimental results You can see this is Mockup X compared to Brandl's analytic lifting line theory on an elliptic wing and just a tapered wing. You can see that the drag coefficient and the lift coefficient match up very, very well, as we would expect. And this is the circulation distribution. These are comparisons to some experimental data. This is on a straight elliptic wing by Smith. You can see that lift is predicted fairly well. Drag, we had some issues with our airfoil model, and so we found that subtracting off your zero lift drag, we came in line with the experimental data very well. This is that same comparison that Jackson had showed. This is showing lift and drag there. I do want to highlight one in particular. This is for, this is a paper that they did. They calculated lift and drag in a wind tunnel on a elliptic wing and a crescent wing with an elliptic chord distribution. And this is the lift coefficient, this is the drag coefficient. You can see that, so the squares are the experimental data and the triangles are data that they're getting out of VS Aero, so panel code. And you can see we're lining up really well with the panel code, again, mostly because we're, this is an inviscid method and we're hitting into stall right here. So we line up pretty well there. And then you can see that once we subtract off this zero lift drag, again, due to just us incorrectly modeling or incorrectly estimating the airfoil parameters, we get really good lineup with experimental data, even better than the high order panel method is doing. So I'll leave it to you to review this paper once it's published if you'd like to know more. But I'd really like to dive in and show you guys how this code works. So you can download it right from GitHub using either you can pull it from Git, or you can just download a zip file of the source code. If you have Python installed on your computer, all you have to do is pip install dot for Mockup X. It'll install all of your dependencies. There's no need to, and it installs it as a module in Python. So there's no need to be copying and pasting executable files. It's accessible from anywhere on your computer. Now, in developing Mockup X, we wanted to modernize things while still tipping hats to maybe the older crowd of engineers, and I won't name any names here, but we've got two different interfaces to Mockup X. One is you can write an input file and you can pass that in through the command line, and it'll just do everything kind of under the hood. And I'll show you how that works, and then I'll show you how the scripting interface works. So you can create an input file that looks just like this. What it does is it tells Mockup X, hey, these are the analyses that I want you to run. These are some solver parameters, and then this is the aircraft and the state it's in. You'll notice that to specify the aircraft, I've given it a file, and I've called the aircraft I'm working on today Goats Flyer. We did this so that if you're running a bunch of different analyses on one aircraft, you don't have to keep copying all of your aircraft parameters between each one of your analysis scripts. You can just store all of the aircraft parameters in one location and then reference that multiple times. And this is what that looks like. You define, some of the geometric parameters, you tell it what controls you have. This is again to ease use. You can give it a kind of I guess I would say a database of airfoils and say, hey, these are the airfoils that I want to use for this aircraft. And that just points it to a file that looks like this, which stores a couple different airfoils and their aerodynamic parameters. And this is again, so you don't have to keep copying airfoil information between each one of your analysis scripts. It's all just referenced to a single file, and it's really user-friendly that way. And then here's where you're adding your wings. Mockup X is purely lifting lines, so you don't have any kind of like pods, nacelles, fuselages. It's only lifting surfaces, but you can add in those effects after the fact in kind of a first order way. But Mockup X, you can specify a semi-span, dihedral chord, the airfoil. With dihedral chord, airfoil, sweep, and twist, you can specify, you can give it tabulated data, and it will linearly interpolate between those two. So you can get all sorts of complicated wing geometries And that's been coming really handy for Horizon, as you'll see in a bit. But MockupX is really versatile to be able to handle really any kind of geometry you want to throw at it. So for this aircraft, I've given it a main wing. I've got a horizontal stabilizer here, and I've got a vertical stabilizer. These names are completely arbitrary. MockupX doesn't care what or how many lifting surfaces you give them or what you name them. It'll take them all in and it'll run the analyses just the same. So I'll show you, that's the airplane file. Going back, this is that input file. So when I pass this to MockupX, it'll run these analyses. It'll display the wireframe of the aircraft. It'll solve the forces. It'll trim it in pitch, and then it'll give me the aerodynamic derivatives. So we do that by doing python -m mockupx, and our input file. I'm kind of partial to ASCII logos, so I designed one for MockupX, but with the help of my sister, who's a graphic designer. But anyway, this is the wireframe of the Goats flyer. You can see pretty standard aircraft, but this is so you can see what's going on. It'll map out the control force surfaces for you as well, and you can see exactly what MockupX is doing. You can even tell it to turn on the trailing vortices. You can see kind of the the wake that's being shed off of that and what that's doing. And then when I click out of this, it'll continue running the rest of those analyses. And now that's done. It spits those out to a whole bunch of output files. I'll show you what those look like. We'll pull up the pitch trim and we'll call up the derivatives. So the result of the pitch trim analysis, and this is just using a standard two-dimensional Newton solver. It's telling me that I need to be at a 2.25 degree angle of attack and have a -1.1 elevator angle of deflection to be trimmed at the airspeed that I gave. And it pulls this off of in this aircraft input file. I've told it what the weight of the aircraft is, and so it'll trim for as much lift as it needs to offset the weight of the aircraft. Or you can alternatively just put in there a fixed lift coefficient, whatever you want, and it'll trim to that as well. Again, really, really, really versatile. We wanted to make this as general as possible. And then this is what the derivatives look like. So it'll tell us what our stability derivatives are, our damping derivatives are, and our control derivatives. So you can get all of your aircraft dynamics out of this. We can look and see, okay, we've got CM alpha is negative, we've got CL beta is negative, and we got CN beta is positive. So we have a statically stable aircraft. So that's how the terminal interface works. Let me show you now how the scripting interface works. And this is where MockupX, I think, really shines, because there's no need to write any kind of wrappers to the terminal. You can just import MockupX directly as a module right here and do all your analyses in Python. So here I've defined the aircraft input explicitly as a Python dictionary. You don't have to do that. You can pull in a file, and I'll show you in a second that works. But this is so that in Python you can work with the aircraft inputs directly through your code without even having to write out to file. It's all just part of the Python script. So I initialize that, and then I'll create the scene, define the state of the aircraft, and then I'll add that aircraft to the scene. And then all this will do is run the same analyses as I did before. So displaying the wireframe, it'll solve forces, it'll trim it in pitch, and then it'll give me the derivatives. And rather than writing these results out to file, I've just asked it to print them to the terminal so I can see what it's doing. This last thing that it's doing, and this is, again, the real power of MockupX having a scripted interface, is that I can do things like plotting a drag polar. There's no need to run a whole bunch of different cases manually and then read in those data files and plot those. You can do it all just in one spot. I've done this in 23 lines of code is all it took to create a drag polar for this aircraft. So I'll show you how that works. And you just run Python script example.py. Again, there's our wireframe, same as what we saw before. And now it's running through those analyses, and instead it's putting out all the results to the terminal. And then there's that drag polar. So this is, again, super simple, super easy to use. And again, this is all documented. I know we're running short on time, so I'll skip on to the next thing that I wanted to, or the last thing I wanted to show you guys, is that you can, having MockupX be scripted, it makes it really easy to do automated optimization. And Zach will get into this more. He's done far more complicated optimization than what I'm about to show you, but This is just a really, really simple example. I'm gonna say, okay, I've got my goats flyer. It looks cool. It's statically stable. Let's find out what our minimum drag airspeed is. And so I've created this function that's called get goats flyer trim drag. All it'll do is initialize the scene. It sets the state of the aircraft based on the velocity that I've passed in. And then I add the aircraft, and here, instead of defining a dictionary with the aircraft, I'm just referencing that file. Again, no need to redefine it. You can just go and reference the file and it'll pull it in. And then I trim it in pitch, and then I get the forces and I return the drag force. And then down here, I've defined an objective function that all it is it gets the trim drag as a function of airspeed, and then it calls a off-the-shelf scalar optimizer to figure out, okay, what's the minimum drag airspeed. I'll go ahead and run that. And as it's running, it'll spit out some results. This is just for me to be able to see what the results of the optimization, or what the optimization was doing, and get make sure it's converging well. So you can see it's trying different velocities and it'll give us different drags. And we've started to converge already down to an airspeed of about 103. We'll see. This converges pretty quick. It should just be a couple more iterations. There we go. So we've using an off-the-shelf optimizer and minimum wrapping of Mockup X. We found out that for the goats flyer, we've got a cruise speed of 103 feet per second gives us our minimum drag. So again, I think I'm really. This is a code that's, it's really useful. It's really versatile. And you can do just about anything you want with it. Zach will show you in a bit that you can take it and optimize, these control mappings based on constraints on yaw, pitch, roll, and your induced drag. Like I said, people have used it to model bird wings, really anything you want. And I've not gone into all of the capabilities of Mockup X. You can read about those here in the documentation. I will show you that a couple of useful things you can do is you can use Mockup X to create solid models. So if you've given it the geometric information for the airfoils, and you could do that just by telling it, hey, this is a NACA 0012. And it's like, oh, okay, I've got the NACA equations, I can handle that. It'll generate an STL model for you, or you can export a step file or a VTK, and then you can take that and pull that into a higher order panel method. Like Flightstream, or like the one we're working on called Mockline, and you can compare, apples to apples of what's going on. Ben will also talk about this a bit more later, but you can use Mockup X to pull out or to generate IGES files describing the curve and the sections of the wing, and then you can pull that into something like SolidWorks and generate a CAD model for your aircraft that you've designed. Anyway, that's all I wanted to share. I've kind of just scratched the surface with Mockup X, but what questions do you have for me?
Any questions? You good? Any online there? Okay, well, thank you, Corey. Corey's a PhD student. Yeah.
So low aspect ratio.
Oh, low aspect ratio. Did we? So Josh Hodson did a bunch of research on low aspect ratio. Did we ever incorporate that into Mockup X?
That's not been incorporated into Mockup X, no. So all of the experimental data comparisons that I did, I think I went down to an aspect ratio of about 5, and it did pretty well at that. People say, the limit of lifting line is about an aspect ratio of 4. So we've taken Mockup X close to that, but.
Okay, thanks.
Uh-huh.
Okay, great. Thanks for joining us, Corey.
Of course.
At home today, he couldn't come in. He had some family obligations at home. So,
Well, I'll be there this afternoon for the flight testing.
okay, great.